Hi, good morning. Welcome to the 16th lecture on topology. In the last lecture, what we did was we started with the topological space X, tau. X is a set, tau is a given topology on tau. Then what we had was a collection script B of subsets of tau. That is subcollection of open sets B, right? Then we defined the notion of a basis for the topology tau, and then we looked at lot of examples. Again, keep it in mind, we started with a topological space. If the topology was also given, then our script was a subcollection of open sets. You understand? Right. Now what we want to do today is something different. We are going to start with the set X, and we are going to start with the script B, a class of subsets of X. Notice that there is still no topology on X, right? Then what are we looking for? Okay, I am given a script collection, script B of X, then I am looking for a topology or some topology tau on X, okay, for which B will turn out to be a basis. You understand that? In the second case, we are starting with just a set and a collection of subsets, no topology in mind. Okay, then what we are going to seek, we are going to find, we are going to discover or create a topology on X. Yeah, and if you had been very diligent watching my first 4 videos in this series, you would have seen about 40% of the topological space examples which I gave. What I had was, I started with a set, I had a script B in a collection, okay, and using that collection only I defined topology. Okay, so in some sense, the examples for today's lecture we are already seen without knowing this terminology, namely a basis for some topology. Yeah, so without much uh, deliberation, let's get into the subject. Okay, please pay attention, this is a very easy concept. Okay, the first one, I start with a topological space, therefore topology is given, therefore I am given a collection of open subsets. Whereas in the second one, I am just given a set and a collection of subsets. I am looking for a topology. Okay, keep that difference in mind. Okay, let's get started. So before going further, let us try to recall one important observation. Let X be a topological space. Okay, let script be a basis for the topology. I want to make some observation about base. Okay, the first thing we did was, okay, X was union of B in script B. Okay, that's the first thing. That's easy, right? And the second thing we looked at was this. Suppose B1 and B2 are script B. Now remember, B is a basis for this. Therefore, this is B is actually a collection of open sets, and therefore B1 intersection B2. Okay, this is my B1, this is my B2. Okay, and this is one open set, the intersection. Therefore, if you give me any X here, okay, and since B1 B2 belong to tau and B is a basis, what do I know? I know that there exists a B, okay, in script B, right? So that X belong to B and B is contained in B1 intersection B2, right? So we want to say that B1 B2, okay, for every B1 B2 and for every X in B1 intersection B2, there exists a B in script B, so that X belong to B1 intersection B2, sorry, X belong to B, that is contained in B1 intersection B2. Right? If you look at the first 4 videos, in many examples I had used this observation, right? Okay, now we are ready for our now we are ready for our journey. So now I am given X is a set and B is a collection of subsets, right? Now the only thing I am asking is, okay, let this be such that it satisfies the above conditions. That is, X is union of B in script B, right? Now what does this mean? This means for every X in X, there exists a B in script B such that X belong to B. That's all this means. You understand this? And second condition is, okay, for every B1 B2 in script B and for every X in B1 intersection B2 there exists a B in script B so that X belong to B and B is contained in B1 intersection B2. Do you follow this? So what are we given? We are given only a set and a collection of subsets, but the collection has these two properties. Yeah. So question is, does there exists a topology tau on X so that B is a basis for tau? Is the question clear to all? Sure? Okay. Now we are ready to do that. Okay. So yes, the answer is yes. How do I define tau? Tau is the collection U of subsets of X. And let me again repeat, in the first 4 videos on examples of topological spaces, we have seen concrete examples. Okay. You should go back and quickly review it. Okay. Not too much time, but quickly review it. Okay. For every X in X, for every X in U, okay, there exists a B in script B that X belong to B and B is contained in. Do you remember? If you had watched the first 4 videos, again you would remember. If XD is a metric space, then how did I define? Okay, there what I had was a concrete example. Now XD is a metric space. Okay, and still I have not introduced no topology yet. Okay, then how did I introduce the topology on X? How did you introduce the topology on X? What we looked at was this script B, which has a collection of all open balls. You understand? And then this had the property. We had 1 and 2. It enjoys both the properties. All these things we have seen. Do you remember? Bx R1 is contained in U1, Bx R2 is contained in U2, therefore R equal to minimum of U1 R1 R2, then Bxr is contained in U1 intersection U2, etc. Do you remember? In the very first lecture itself I made the point, whenever I had a collection B with these two properties, I can define a topology. Okay, go back, pause, review, proceed. Okay, so let us verify. Tau I define is a okay. Now I want to say whether we will check verify this a topology. Okay, what are the things I have to check? The empty set. Remember, the empty set always belong to tau. Why? Because what I have to do? You give me an x in empty set, then I have to find a b. Alright, if you say empty set is not in tau, let me repeat the logic so that people who are not familiar with our foundation lectures will learn it. Okay, if you say some set, okay, a is not in tau, what does it mean? That means, okay, if a is in tau, for every x something must be true. That means if a is not in tau, meaning there exists an x in a, so that this is not true. Whatever b you give me, okay, whatever b, for every b in script b, so that x belong to b, but b is not contained in u. Okay, you give me any b which contains x, no b is such a b is going to be contained in u. You follow that? Right. Now empty set belong to tau, because if it is false, then you have to start with an x in the empty set so that something happen. So you can't do that, therefore empty set belong to that. And capital X belong to tau, that's because of condition 1, because x is union of, I already reformulated that, right? Yeah. You remember what is the meaning of this? Okay, this one clearly says x is, okay, x belong to this, because you give me any x, then there is a b, so the x belong to b, and b is contained in capital X. Okay, this is all right. Okay, so this is because of condition 1. Right, now next thing, let us start with the collection UI. I want to know whether, okay, so now let's look at that thing. Suppose UI is a collection of tau. I want to know whether union UI is in tau. Okay, but that's again easy, right? Now by now all of you 15 lectures are gone, all of you should be confident. You give me an x in union UI, that means there is I, that the x belong to UI, and UI belong to tau, that means there exists a b in script b, so that x belong to b, and b is contained in UI, and UI is contained in union U. Okay, therefore this is also true, right? And let's come to intersection, and this is where we are going to use the important property. Suppose u and b belong to tau, and let's look at u intersection b. I want to know that it belongs to tau. So how do I know something is in the topology? Start with any x in u intersection b, right? Then I want to know whether there exists a b, so that what happens, x belong to b and b is contained in u intersection. This is what I have to find out. Okay, I have to do this, right? But remember, x belong to u and u is in tau, is a okay, in the, that what does it mean? There exists a b1, so that x belong to b1, sorry, x belong to b1 and b1 is contained in u. Now what do you think I should do next? I'm sure all of you know that, right? X belong to v, there is a b2, so that x belong to b2 and b2 is contained in b. Now how many of you can guess the proof, complete the proof now? Right, because x belong to b1 intersection b2, therefore by condition 2 there is a b in script b, that x belong to b and b is contained in b1 intersection b2, right? But b1 intersection b2 is contained in u intersection b. Therefore for each x in u intersection b, I have found a b, so that b is contained in u intersection. This implies u intersection b is of tau. So pause. Yeah, so what have you done? Just let's quickly review. I start with a set and a collection b in subsets with which satisfy property 1 and 2. I won't repeat. Then we constructed a basis, sorry, we constructed a topology on b. Let's see, topology, sorry, topology on x. Now next question is b a basis for tau? Of course, by very definition. Why? Because the moment you say, when do I say, so if you give me a topology tau and a collection B, when do I say this is a basis? Give me any U in tau and any X in U, then I have to show that X belong, there is a B in B, that X belong to B and B is contained in U. But that's how we define tau. Do you understand? Okay, a resounding yes. Okay, so we are done that. Now let's do that. So you want examples? As I said, okay, review the first 4. In this series. To quickly recall, let me just give, okay, for example, if XD is a metric space, okay, then we collect this open ball, then we get a metric topology. Okay, this is the first example. And second example, I do not know how many of you have seen, okay, infinitude of primes, then this my X was this, then what I had was this script B was a collection of, okay, thing, okay, all cosets of non-trivial subgroups of Z under addition. Then we define a topology. Third, my X was R and script B was all the elements of this kind. Then the topology we had was lower limit topology. You see that at that time I did not even say that, because you had already seen this is A and B. Now what are the possibilities? If I have CD, CD may be like this, or CD may be like this, or CD may be like this, or CD may be like this. Okay, in all the cases the intersection is again an element of the form script B itself. I don't have to find a script B, right? Because actually what happened was in all these cases B1 intersection B2 is again an element of script B, right? But that was not the case here. Okay, I have 2 open balls. If they intersect, then I have to find, for everything I have to find an open ball. You understand that? Whereas in this case, third case, okay, intersection of 2 elements from the script B is again an element of the script B. Just this is only to, I want my students to think. It's not just simply accepting it. You should compare and contrast so that you learn all those things. When you are comparing 2 things, then you are learning 2 things also better, and you are finding some contrast between them, then you understand them in depth. Okay, that is why I always do that, give analogy, compare with various things. You can stick to only one problem and do it. It may look very clean and neat, but your idea will be very, very narrow. Okay, right? But now I want to tell you the most important thing you did something fantastic. Okay, there are a lot more examples. Okay, I don't want to give, but this is already I had given 3 examples. Okay, please go through this thing. So in all these cases, I start with a set, I add a collection script B. Okay, if you want fourth, okay, I will also say. Assuming that you have done that, okay. Fourth example is where I was interrupted. Okay, so I said something. So let's X this be an ordered set. Remember, it's a total ordered set. Okay, so I want people to have watched my order topology one video. Okay, if you didn't, you can skip this. Then you don't have to worry about. Okay, then what we did was we defined order topology there. Okay, but instead we can also get this collection A B. Okay, A and B are in X and A less than B, assuming X has no maximum and has no minimum. Okay, if it has a maximum and minimum, then I have to add, okay, minimum B, okay, B is in X, and union A M, where M is the maximum. Okay, then what we did, okay, it is easy to check that script B is a basis for some topology. Okay, so what really happened in all these cases is something very interesting. As I did earlier, if I take B1 and B2 in script B, it is easy to check B1 intersection B2 is again in script B. In many other good interesting cases this happens, but remember, in the case of matrix spaces, that was not the case. Yeah, maybe I'll say it again here instead of searching for that. Okay, suppose I had a matrix space xd. This is an aside, but as you know that I always try to think. Okay, then this script B is collection of open balls bxr, then we saw, so I have this open ball, this is an open ball, then this is my b1, this is my b2, then for this x, then I have to put on something. You understand that? So b1 intersection b2 is not in script B. You understood that? But in this case it happens, in many cases it happens. Okay, anyway, so this is the basis for some topology. That topology is called the order topology. Go back to the way we define order topology. What we claim is this is the basis for the topology. Okay, and the next example is the most fascinating example, which will come to the next one. Was, remember, I had a set X, just a set, and I had a collection A of P of X, collection of subsets. Then what we did was, we know there exists a smallest topology tau A containing A, and we had given a very explicit concrete description of tau A. Just to quickly recall, how did you define tau A? Tau A was set of all subset U of X, so that for every X in U, there exists a finite subset F of script A, so that X belong to intersection A in the finite subset, and that should be contained in U. Okay, as an MSc student, and more than that, you should learn how to work with this kind of thing rather than always enumerating A1, A2, AN kind of thing. For those who are still uncomfortable, let me just say that, okay, for every X in U, there exists A1, A2, AN in script A, so that X belong to A1 intersection AN, okay, that is contained in U. Notice that this N and A's depend on the point X. Yeah, if you are very comfortable with this, use this also, no problem, right? This was the explicit description. What really happened was the following. Okay, let us look at B to be the collection of all finite intersections of elements from A. That is, this is collection B, a subset of S, so that there exists A1 AN in script A. Again, I can use the finite family F, okay, so that B equal to A1 AN, right? This is a collection. Then what we saw was B satisfies 1 and 2. Therefore, it is okay. B is a basis for some here topology. For some topology, call it tau. What we claim is tau u and tau a are the same. Okay, this is what we proved. Okay, yeah. So we claim the script B is a basis for tau A. Therefore, we actually did, if you notice, okay, without saying I had a script B, okay, please follow me, okay, do not be intimidated, okay. What I did, I directly gave without introducing a basis. So what I have is, I have a script B defined like this, finite intersection. Then I say it's a basis for some topology on S, and that topology is the smallest topology containing A. You understand? What we did was we directly defined the topology to A. We understood? Do you understand this? Let me just check why script B is a basis for some topology. Okay, we want to understand this. The first thing, okay, is script B. Script B satisfies one, because union of script B. Notice that script B contains script A. Why? Because when I take n equal to 1, then a1 intersection a2 intersection an, that is A, right? Given any A in script A, take a1 equal to n equal to 1 and a1 equal to A, then A has to be in script A, right? Okay, you follow that, and hence union of B in script A contains union of A in script A, but that's already X. Do you remember our condition on script A? Therefore, once it satisfies one. Do all of you agree with that? And second, that's much still easier. Suppose B1 and B2 belong to script B. Then what do I do? Let X belong to B1 intersection B2. Right? Then I want to know whether there exists a B in script B, so that X belong to B and B is contained in B1 intersection B2. Yeah, but that's very easy. Why? B belong to B1. B1 belong to script B. That implies B1 is already of the form some A1 intersection AM, and B2 belong to script B. That implies B2 is of the form some A1 dash intersection AN dash, where AI and AJ dash, they are all in script B. Because remember, B1 B2 must be finite intersections of elements coming from script A. Therefore, what is B1 intersection B2? That is A1 intersection AM intersection A1 dash intersection AN dash. Are you following? Therefore, that is how the form A1 double dash intersection AM double dash intersection AM plus 1 double dash intersection AM plus n double dash, where A1 this is equal to this, and this and these are equal, this and this, right? Therefore, this is again B1 intersection B2 is already in script B. Therefore, what is the xi? What if you give me an x in B1 intersection B2? What B I will choose? Choose B itself, B1 intersection B2, because that is in script B. You understand? So that's a basis for some topology. Okay. So if you compare the way we define tau A, state tau, okay, and then for some topology tau, that topology tau is nothing other than tau A, because look at the way we define tau A. For each x in U, there exists A1 to AN, that x belong to A1 intersection A2 intersection AN, that is contained in U. But this is same as saying there is a B, x belong to B, B is contained in U. That means U is in tau. You follow that? So this is clear. So without introducing the basis, notion of basis, a basis for some topology, I defined a concrete way. You may wonder why I did that, because see, when I introduce a basis, it looks all well and good because it's a jargon, it's behavior. But in reality, whenever I script A, I want to deal with tau of A, the smallest topology containing A, this definition will be the most useful. Believe me, as I said, when I define tau A, this definition, this concrete description will play a very, very crucial role when we learn about new topologies from the old topologies, as we go along with respect to product topology, quotient topology, and whatever. Okay, please learn that well. And the last example is the sixth example. Suppose x1 tau 1, x2 tau 2 are two topological spaces. Okay, you might have seen we already did that. Okay, again, this is an example which I did in the first 4 lectures, right? So I want to define now x1 cross x2 is just a set. I want a topology on that. What I did was I looked at script B. Okay, this is a collection of the form u1 cross u2 where ui belong to tau I. Okay, and this is if you remember, this is what I did. This is my x1, this may be my x2, this may be my u1, okay, and this may be my u2. Then the topology was this. I'm drawing other pictures are in you know r cross r kind of thing, but this is a very common thing. Okay, don't worry about x is something unknown, y is something not known, etc. But this gives you an idea. So one usually calls this rectangles because of the picture, right? Because in the case of r, if I look at the basic open sets will be open intervals, then r cross r, this will be rectangles. That's why we call it the rectangle. Now what we saw was this is a basis, could be, is a basis for some topology on x1 cross x2, and that topology is called the product topology. Okay, this we had already seen. Okay, the script B satisfies one. This is easy. Okay, go back, check it. Now suppose I have something like now the u1 cross u2, v1 cross v2. This is my b1, this is my b2. Then we have checked what is b1 intersection b2. This is just set theory. Yeah, that is again of the form some w1 cross w2. Therefore it belong to b. Okay, this is just set theory. Take verification. I have done it in one of the first 4 lectures. Please go and verify. So for product topology also we can get it. Now remember, on x1 cross x2 is just a set. We did not know how to define a topology. So what we did was we looked at some example. So all these things you can see show something very basic trick. What is the basic trick? I have a set x. I want to give a topology on this. Then what happens is there is a very natural collection script B of subsets of x. Okay. For example, let's look at this here. It is just u1 cross u2 where u1 is open in x1, u2 is open in x2. And similarly in the order topology, take A and B, A less than B, let's look at open intervals. These are the naturally occurring things. And this script B satisfies the condition 1 on 2, then we can generate a topology. So, okay, please learn these things well. So I have given you quite a few examples, and I hope you understood the difference between basis for the given topology and basis for some topology, right? And again, what we did was, without even knowing these words basis, etc., basis for some topology or whatever that concept, we already had constructed lot of such. We use this notion, this concept to generate lot of topologies, to equip some sets with some topologies in the lot of examples. Okay, some other thing is not in this series, but they are separate, like order topology and the topology of arithmetic progressions on Z. Okay, these are all two separate videos. They are not in the part of the series, but if you are interested in topology, you should also learn them well. Okay, I hope you enjoyed. We will meet again with something new. Okay, take care, stay safe.